Okay, so last time we were talking about examples of systems with continuous symmetries, and we talked about magnets as a simple example, systems which have spins, but instead of the spins just pointing up or down, the spins can point in arbitrary directions, so they can point in arbitrary angles, so you can rotate them by an arbitrarily small amount, and so they have a continuous symmetry. And then at the end of the lecture, we talked very superficially about the case of helium-3 superfluids. So superfluid helium-3 are bosons, they're composite bosons, they're made up of pairs of helium atoms, which are fermions. They normally will repel each other through hardcore interactions, but at sufficiently low temperatures, spin interactions can stabilize the helium-3 atoms to form a kind of molecule, a bound state called a Cooper pair, which is a composite boson. So think of it as two helium-3 atoms inside a big balloon. The big balloon has bosonic symmetry, and if it's a boson, then it can undergo Bose-Einstein condensation. And the question is, if I look at this Cooper pair, what is the angular momentum states of the helium-3 atoms in that? Now, normally, we're not going to talk much about superconductivity in this course, but normally if you have a superconductor, you have two electrons. They're very far apart, typically 1,000 angstroms, something like that. And so they can be in an S-wave state where they form a Cooper pair. They attract each other by exchanging sound waves, quantized sound waves, and they form a molecule which can be in its zero angular momentum state, so L equals 0, so that's known as an S-wave state. But in helium-3, because they're short range, they can't do that, because if they were to be on top of each other, the hardcore repulsions would raise the energy and it would be much too high. So they're not going to be in the lowest angular momentum state. They're going to be in a state that's orthogonal to that, and all the higher angular momentum states are orthogonal to that. So then it turns out that the spin and orbital angular momentum are both L equals 1. And so that means you have, for an L equals 1 state as an angular momentum, you have L equals 1, L equals 0, and L equals minus 1 as the states of the system. And so what happens is then you can form a system with 3 times 3 times 2, which is 18 components in its order parameter. And the order parameter has got the 2 because you have a wave function that describes a macroscopic occupation of the ground state for the superfluid. It has real and imaginary parts, so that's why there's 2 components for that, and then 3 by 3 for the orbital and the spin angular momentum. So you've got an 18-component order parameter. So you can have an incredibly complex structure in systems with continuous symmetries. Okay, now what I want to do today is I want to get away from looking at spin systems or looking at systems with a microscopic level of description, and instead I want to talk about a top-down level of description. So bottom-up level of description says the world is made of stuff, atoms, molecules, strings, quarks, whatever it might be, and then I want to know, once I describe the system like that, what its properties are. The top-down way of thinking about a system is to say, well, what is the system? So symmetries, can we describe the physical system without actually knowing too much about the microscopic behavior of the system? And that's what I want to teach you now. That's called phenomenological Landau theory. And we're going to see that Landau theory is our most powerful and useful tool for describing ordered states. Not only is it a powerful tool for describing ordered states, but it's also incredibly easy to use, requires very little mathematical sophistication, at least conceptually. So I'm going to talk about Landau theory first with respect to spin systems, spin half systems, which have a discrete symmetry, up-down symmetry, and then we'll talk about the extension of that for systems with continuous symmetries. And if we get time today, I will talk about how one computes correlations in such systems. Okay, so let's then get started. So phenomenological Landau theory. So that is in my renormalization group book, chapter 5.3 to 5.6. And what we're going to describe then is how to describe systems based purely on symmetry without knowing anything. This is the if you will, the something from nothing magic of this course. Okay, so those of you who took my earlier course, actually nobody here did. Oh, you did. Yep. So one person here in the room did, and I know somebody else who's taken this course before took the renormalization group course. So one can start off with a microscopic description of the system, and then in a systematic way can derive a coarse-grained level of description with a lot of calculation. So we're not going to do that. We're going to do something much smarter and much more interesting. So let's get started. So we're going to focus on different levels of description. So what I want to show you is this. Let's suppose that I have here we go. Let's suppose that I have a spin system. So I'm going to suppose that I have a spin system which will draw as if it was in one dimension. So I've got a bunch of spins like this. That's a microscopic configuration. And I might say that this is a fine description of the system, but it's much more detailed than I need. Just like if I said I'm going to describe the gas in this room, and I said I'll tell you where every molecule is in this room, and I'll tell you how fast it's moving. Would you like that? You'd say, hell no, that's far too much data. I wouldn't know what to do with it. So this level of description, the microscopic level of description, has a big problem. It is useful, it's precise, but it has too much information. So we'd like to have a compressed description of the system. And so what we might say is, well, why don't we do this? So what we want to seek is a compressed description of the system. And so what we might say is, well, why don't we average locally and construct a continuous function, smooth continuous function, that describes the local average order parameter. And we know that the order parameter in this particular case is just a magnetization. So if you want to think about what the analog would be for the air in this room, you could look at all the gas in this room. I could tell you the position and velocity of every single particle in this room. You say, I don't want to know or anything to do with that. What I want to know is what is the local density? What is the local pressure of the gas in the room? And if I knew that, then I could say, well, now I understand how you're listening to me talking, because I'm sending sound waves to you, and those sound waves are local oscillations of the density of the gas. And inside the local regions of where there's high density and regions of low density, there's a huge number of atoms. And so I don't need to know about the positions and velocities of all the single atoms. So the analog of this analog of local density in a gas, for example, in a compressible gas. And why do I want that? This is actually useful it's a useful level of description because I can use it to describe sound waves. And what's important here is that the wavelength of the sound waves is much greater than the mean separation between the atoms in the gas. And so because I can do that, then I can make a description of sound waves, and that description is known as a hydrodynamic description. So that's what I'd like to have, but I'd like to do this not just for sound waves. I'd like to do this for any system, however complicated it might be. So in our particular case, our order parameter, I'll denote it by eta, but it could be anything. But here, just think of it as being the magnetization. So it's going to be eta is 1 over n sum over I equals 1 to n. SI, and that is just the magnetization. So this, the way I've described it so far, is an average over the system size, so it contains no spatial information. So what we're going to do instead is slide a window along our system and locally average the spins in that window. So over here on the left-hand side, I'm going to draw such a window. So there is my window like that. I'm going to imagine that this thing has its center of mass at the position R. And then what I'm going to do is I'm going to say, well, this thing has a size, which I'm going to call capital lambda. And I'm going to ask what happens if I compute the magnetization inside that sliding window. So the idea is compute the local magnetization in that window at every point in space. So what I do is I compute m. It's going to depend on r. And what it is then is 1 over n lambda, the number of spins inside that window, times the sum over I equals 1 to the number inside that window. And then the SI, and those SI live inside the sliding window. I don't know a mathematical notation that's trivial to write it down, so I'll just write it down like this. So what I do is I put that the center of mass at the point R. I calculate what the magnetization is. So here it's 1, 2 up, 1 down. So that's 1 up, 2 up, and then 4 down. So it's about -2 down. There's 6 spins in there. So it's -2 divided by 6. So it's -1/3. Okay, so I can get a number. So this is going to give me then a number m of r. And of course, m of r is going to depend on how big the window is. So I'm going to denote that dependence like this. And then now if I were to move that sliding window to the right gradually, I would have different spins entering into that window. And so I would get a function that looks, that is a continuous function of space. And it would look something like this. I can't promise you that that what I'm going to draw is the exact function for what I drew there, but it's going to be some function which is continuous and smooth and sort of does something like that, and goes between -1 and 1. Okay, so that's the idea of writing a coarse-grained order parameter. So we're going to call this coarse-grained order parameter. And it's a local object. And coarse graining just means averaging over some little blob and then moving that blob along. Okay, so that's great. So now we want to ask a statistical mechanics question. So in statistical mechanics, what do we always ask? We want to ask is, if you give me the configuration of the system, given the configuration of the system, what is its probability? So that is the fundamental question in statistical mechanics, and we know the answer to that. So if we're looking at the microscopic level of description, we would just say, well, it's the Boltzmann answer, it's the Boltzmann distribution. So P of SI, you tell me all the spins, up, down, up, down, up, 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 whatever, 10 to the 23 of these things, then we know the answer to that is e to the minus beta times the Hamiltonian of the system divided by the partition function. And as we said before, that's way too much detail, so we don't really want that. But in principle, there it is. So now the question is, what is the analog of this? For the coarse-grained description. So suppose you just gave me the curve m lambda of r, and you said, well, tell me what is the probability of that, then the answer is the following. So the question is, what is the analog for that? And so let's just write it down. So I'm going to tell you what the answer is. So in the case of, say, the local magnetization, I'm going to say that this is going to be e to the minus beta times a Hamiltonian, an appropriate Hamiltonian. We don't know what that Hamiltonian is, so I'm just going to write it down by the symbol L. And then we want to divide by the partition function. So by analogy with what we did with Boltzmann statistics, Boltzmann distribution, we're going to have exactly the same thing for our coarse-grained description. But now our partition function is going to be the trace. So I'm going to write the trace as the sum over all variables like this of e to the minus beta L of m of r. Okay, so that's my answer, but of course it's a useless answer because I haven't yet told you what L is, and I haven't yet told you how to evaluate the partition function. But remember that when we derived the Boltzmann distribution back on your mother's knee, you didn't really say what was special about the degrees of freedom. You didn't say what was special about the Hamiltonian. So the arguments that you used to describe and derive the Boltzmann distribution would also apply for any other level of description. So the answer has to be like this. And so this is fine, but useless. And why is it useless? Well, we don't know what is L. And we don't know how to evaluate the partition function. So now we're going to talk about how to solve those problems. So first of all, let me just give you some nomenclature. So this, when I write down this, what this means is the trace over m lambda of r. Okay, and what trace means is sum over all possible degrees of freedom. So in this particular case, the degree of freedom m lambda of r is a continuous function. And so what that means is that we're going to have to interpret this as not summing over all degrees of freedom of a discrete spin system, but interpret as integrating over all possible smooth continuous functions. And that is the analog of summing over all possible discrete states of a spin. So that's the first thing. And we give a name to this, and so the name for this is functional integration. I'm going to teach you how to do it, and it's not as hard as it sounds, but it requires some work. Okay, question.
M lambda depends on R. What is R?
R is the space, right? Remember that here's space on the bottom left. When I slide this window along my spin configuration, it changes as a function of space.
Okay,
right?
Makes sense. And lambda is just the notion of the sliding window.
Lambda is what I've drawn there. It's the size of the sliding window.
Right.
Okay. So I haven't yet told you how to do the calculation, but that's what we're going to have to do. Yes.
When we talk about all possible, we talking about we can define different definition of an M.
Can we define different definition of what? I will explain you how we do the calculation. Don't worry too much about that. I just want you to know that conceptually, whereas before we summed over all possible configurations of the spins, I had n spins, each of which can have two states. I've got 2 to the n possible spin configurations, right? If I have a continuous function in space, I have an infinite number of possible configurations of functions that are smooth and so on, and we're going to have to figure out a way to make this a meaningful mathematical concept. And I'll show you how to do that. It's not as bad as it sounds. Okay? Any other questions? Okay, so we're going to leave this question of how to calculate this. So then what we're going to do next then is we're going to say, okay, well, how do we construct the L? How do we calculate this? There's something which is like playing the role of a Hamiltonian L of m lambda. Okay, so that's the thing. The next thing we need to know, if we know how to calculate it, that wouldn't be very useful if we don't know if we don't know what the function is. So the answer is we don't calculate it. Okay, it's virtually impossible to calculate. Okay, so we're not even going to do that. But we can figure out its structure based on simple arguments. And these simple considerations are provably correct when you're very close to the critical point, and they are semi-quantitatively correct when you're not near the critical point. So we're going to go with semi-quantitatively correct because Perfection is the enemy of the good, and we just want a good description. And it'll be good enough because most of what we need, we don't need any of the details in any case. So again, in the nomenclature here, so this thing L is called the Landau free energy. At least if it's in equilibrium. And if you're not in equilibrium, then there's another way that one can construct this one, but one doesn't use a partition function. So what we're going to do now is we're going to use symmetry and analyticity to construct L. Okay, so what are those principles? So the first thing is that we have an order parameter which I'm generally going to write as eta lambda of r. It's coarse-grained over some scale lambda. It depends on space, and it's something which could be scalar or whatever it might be, but we're not going to say necessarily what it means. Okay. Second thing is that the state of the system, just like in thermodynamics, state of the system, i.e. eta lambda of r specifically in equilibrium, is obtained by minimizing. In equilibrium at 0 temperature, it would be the energy. If we were at finite temperature, not infinite temperature, but a finite temperature above 0, it would be the free energy. And so here it's obtained by minimizing L, this Landau free energy. So basically dL by d eta is equal to 0. And then once I know that, then that gives me the value of eta. Okay, so that's going to be the idea. Next thing is we're going to expect that L reflects the symmetries of the system. So for example, let's suppose we had an Ising magnet. As usual, we know that has a spin flip symmetry, time reversal symmetry. So we would expect that the Landau free energy as a function of the magnetization is also invariant under the order parameter going to minus m. At least in an external magnetic field that is equal to 0. So if we knew that, then if that's true, then what that means is in this particular example, L of m is an even function of m, at least if external magnetic field is equal to 0. Okay, so we can use the expansion as a way to construct L. So what we then expect then is that this means that we can write that the Landau free energy is a power series expansion in the order parameter. In this case, L is going to be something like eta squared plus eta to the 4th plus e to the 6th, and so on and so forth. So that's the first thing. Okay, so that's principle number 3. Principle number 4. Let's first of all suppose that the system is spatially uniform. For simplicity. And then later, put in the spatial structure. I'll tell you why that makes sense in a few minutes. Okay, so then if that's the case, then this Landau free energy must be proportional to the volume of the system, or maybe the number of sites in the system. But remember, once we've made this coarse grain description, we don't anymore have lattice sites. We can't even see the existence of the lattice sites. So we'll just say it's the volume of the system times a Landau free energy density. So we're going to write it like this, and then we're going to say that L is some power series expansion in n equals 0 to infinity, some coefficients times eta to the power n, and we're going to construct what those coefficients are. Okay, so that's the basic idea. So the next piece of information that we need is that eta is an order parameter. So it's a quantity that tells us whether or not the system is ordered. If eta equals 0, that implies there is no long-range order in the system. If eta is non-zero, then that implies that there is long-range order. And the bigger eta is, the bigger is the level of order. So what that means is that in the phase, in the high temperature phase, where T is greater than the ordering temperature Tc, then that means that we want eta to equal 0. So the eta equals 0 must be a solution of dl by d eta is equal to 0. Okay, and we'll see what that means in a minute. And then in below Tc, we know that eta should be non-zero. So a non-zero value must be a solution of dl by d eta equals 0. Okay, so we're going to work that out. So the next thing is, let's suppose we're near the transition. Now, in this course, we're not so interested in being near the transition, okay? But that won't make much difference for what we're going to do next. So let's suppose for now that we are near the transition. Then what that means is that eta is going to be very much smaller than 1. We're expecting that the level of order, once I just go below the ordering temperature, is going to be very small. There's going to be just a few spins that are pointing up rather than pointing in the other direction, a small excess in one direction rather than a huge excess. So this is a continuous transition. So we're going to assume that eta is very much less than 1. And if eta is much less than 1, then that means that we can truncate our power series expansion. So you might say, okay, well, where do you truncate it? So should we truncate it at order eta squared? Well, that's not going to have enough information. If you stood at e to the fourth, you'll see that that's going to be just right. If you truncated it at e to the sixth, you've got redundant information. So it will turn out, so we'll see. It turns out that eta to the fourth is good enough. And why it's good enough, you'll see in a minute. Okay, so what that means is then that what we've just decided then is L is the sum from n equals 1 up to 4, some coefficient an times eta to the nth power. And well, this is really L by my definition. And so the first thing is that we determine L, we determine eta by dl by d eta is equal to 0. So that means that a1 plus 2a2 eta plus 3a3 eta squared plus 4a4 eta cubed equals 0. Okay, so that's the extremal equation. So now we know that above TC, eta equals 0 must be a solution. It's an order parameter. And so that means that the coefficient A1 must be equal to 0. So we can get rid of that. Okay, so that one, we're not going to need to worry about that one. Then the next thing is that we have symmetry. So what does the symmetry tell us? Well, when h is equal to 0, the probability distribution of any state with order parameter eta must be the same as the probability of the system when eta has got a minus sign in front of it. So that means that L of eta must be even. And so that means that A3 equals A5 equals A7, etc., must be equal to 0. So now we've only got two terms. So now what we've ended up with then is that L must be of the form A2 of eta squared plus A4 eta to the fourth. And what do these things depend on? Well, these coefficients do depend on temperature. So we're going to see that this one does have a temperature dependence that we're going to need to worry about. And A4 is not going to need a temperature dependence. So even though in principle, this does depend on temperature, in fact, it'll be good enough for most purposes to set A4 of T is equal to a constant. Why? Because I can just do an expansion about T equals TC, and then I'll just do a power series expansion of the coefficients and powers of T minus TC, and so those will be higher order corrections to the things that I would like to calculate. Okay, so if you're with me so far, then let's give you a quiz question. So here is a quiz question. So we saw that the Landau free energy has to be an even function. So an a squared, a to the fourth, and that's even. Why didn't we say, well, okay, I can make a function that is lower order in eta and which is still even. Okay, so here's our quiz question. We want eta to be much smaller than 1. So why did we not take eta as a function that is symmetric? and eta goes to minus eta. So you could have said, well, we want an even function. Well, I can write down an even function that is higher order, sorry, that is lower order, the leading order compared to eta squared, which is eta. Remember, the smaller eta is, the lower terms you want to be important. So the linear term you would think would be the one you would need. And so why didn't we take the absolute value of eta? That's the obvious thing to take, but we didn't do it. I just pulled the wool over your eyes and said we start with eta squared and e to the fourth. Why couldn't we have done that? So how many people here know the answer to my question? I'm pretty sure some of you know the answer because I've told it to you before. You know it. Yeah. Okay. So then you can be quiet. Okay. But how many people here don't know the answer to my question? Okay. So those people, which is most of you, try to figure it out. Why didn't we use absolute value of eta? So you can discuss it with the person sitting next to you if you like. So you have and you two have. You're welcome to go over there and discuss it with those two on the other side of the room, if you'd like to discuss it. Do you want to discuss it with the other two students? Go and say hi. Go and wave at them. Say introduce yourselves. Say your names, and then see if you can figure out why we didn't have this extra term. And if you know the answer, don't tell the others. Okay, any progress? Who doesn't know where to start in trying to answer this question? Who wants a clue? Anybody there want a clue? Do you people on the second row want a clue? A hint? You want a hint? Okay. Well, so think about this. How did we construct, what is this thing meant to describe? And what it's meant to describe is shown here on the left. Right? It's meant to describe what happens when I take my sliding window and move it around in space and calculate what's going on in that. Okay, I'll give you another clue. Remember that the thing we're trying to construct is a free energy. It comes into a partition function. We're doing statistical mechanics. Okay, so we're summing over configurations or something or other. So So that's what we're doing. If we were to construct this L from first principles, that's what we were doing. Okay, everybody on the back row at the right there, you look like you're either in a mosh pit at a heavy metal concert, or you think you know the answer. Can you speak up so everybody can hear you?
The absolute value is not an analytical function, so
Okay,
not good.
so why couldn't it be that?
The second derivative will be this.
That's true. It is not an analytic function. Okay, so the first thing is if I plot absolute value of eta as a function of eta, what does it look like? So it looks like this, something like that, right? That's absolutely true. So what? So what's wrong with that?
So is it somehow problematic for the derivative of L with respect to eta to be finite when eta is very small?
Not particularly. I mean, after all, what we expect for remember that for phase transition behavior, say as a function of temperature, what we expect is that this thing is going to do this. So it's certainly got some weird behavior round about here. Okay, so think about this. So we've agreed that this function is not analytic. So EJ is exactly right about that. But why couldn't we get that from the way that we constructed, that we supposedly mentally think of what this thing represents? Okay, so I'm going to reveal a bit more. So you got halfway there. So the second question is, why is having a non-analytic term in L a problem? And the answer, so you knew the answer. So why didn't you do the big reveal?
So if you write down an equation of state, which is the partial, like the derivative of the L with respect to eta, you get a discontinuity in the equation of state at t equals 0. So you have a discontinuous curve for like some series expansion of eta. It doesn't show like phase transition behavior. If you are expecting that like eta equals 0, it goes from 0 to like some finite value. That is not what you would like get if you have a discontinuous function. You write down the equation of state. Okay.
Well, I understood most of what you said, but that's not what I think is the answer. Okay, that again is an explanation based on what's wrong with the outcome, not how you actually got this form in the first place. So what I want you to remember is that what we're doing in constructing this is we're dividing our system up into localized regions, these oval windows that you can see there on the left. And we're taking that little window and we're sliding it along. So when we are doing that, we're computing at each point of space, what is the partition function for that little set of spins, and we're computing what its free energy is. That's locally what this Landau free energy is telling you. So the point about it is this: when we construct the partition function, we construct the free energy that's always some trace over the degrees of freedom of the microscopic spins. So we're summing over a set of terms which are e to the minus beta times an energy. And in this particular case, when we're looking at this coarse-grained region of dimensions lambda, we're summing over a finite number of spins. So here's a little region of size lambda over here. It has, say, 20 spins in it. I'm doing a sum over the states of those 20 spins. I move it along to the next site, do the same thing. I'm doing the same thing with those ones, and so on and so forth. Each point in space, I'm summing over 20, in my example, 20 spins. What am I actually summing over? I'm summing up terms which are e to minus beta times energy. E to minus beta times energy is an analytic function. So I'm summing up a finite number of analytic functions to compute what the free energy is at that point. And so what that means is that if I'm summing up a finite number of analytic functions, that has to be an analytic function itself. And when I say analytic function, I mean in the sense of complex variables, that it has a power series expansion in the complex plane. So what that means is that because my coarse graining region has a finite extent, I'm always summing up a finite number of factors, e to the minus beta times an energy, and so I have to get an analytic function. So when I compute what my Landau free energy is, it has to be analytic in the order parameter. So let me write that down, and then I want to go on. So it's a very subtle point, but it's very important in the way that we construct these things. So explanation. In each coarse-grained region of size lambda centered on a point in space R, we have a finite number of degrees of freedom. In this case, spins. And that means that when we compute the local free energy, i.e. the local partition function, it is a sum of a finite number of terms, each analytic, i.e. of the form e to the minus beta times some energy. And so what that means is that L of eta must be an analytic function. And that means that this is not an analytic function, and so we can't use it. So it doesn't mean that this description is not able to give us non-analytic functions. It is, but how it does that is very subtle. Okay, so now we've done the quiz question. Now let's have a look at the term A4. So what about the quartic term? So that's the highest order term in our Landau free energy. And as eta gets bigger and bigger, well, we want the Landau free energy as a free energy to be reflecting statistical mechanics. We want it to be bounded below. Okay, systems always try to minimize their free energy, so we don't want anything to go to minus infinity. So what that means is, in order that L of eta is bounded below, i.e. does not go to minus infinity when the absolute value of eta goes to infinity, we need a quartic term must be greater than 0. Okay. Because we don't want E2 equals infinity to be a solution. All right. So now let's go back. So this page 57 is really page 56, apparently. Okay, so now let's have a look at what happens. So again, so now we're going to look at the quadratic term. So what we have is L is equal to A2 eta squared plus A4 eta to the fourth. That's all we have now. And we know that dl, well, this is curly L, dl by d eta is equal to 0 is 2a2 eta plus 4a4 eta cubed, and that's meant to equal 0. So what we want is for t greater than tc, eta equals 0 is the only solution. So that means that we need A2 to be greater than 0, and we'll see why in a minute. For t less than tc, we want eta to be non-zero is a solution. And for that to happen, that means that A2 must be negative, because then what we get then is that eta squared is equal to minus A2 over 2A4, where A2 is negative. And that then is a positive number. And so what that means is that A2 changes sign at t equals tc. And so therefore we can expand A2 as some constant plus A21 t minus tc over tc plus A22 t minus tc over tc squared plus higher order terms. And because we need because A2 changes sign at TC, that tells us that this coefficient A20 in the Taylor series expansion must also be equal to 0. So therefore, we now have derived at the following result, that L for general terms must be some coefficient, which I'm now going to call A, times T times eta squared plus 1/2 b eta to the fourth. And here I mean T, it's not time, it's T minus TC over TC. This B is a coefficient that is just some number greater than 0. And this has to be a functional form of the Landau free energy near the phase transition. So it is inevitable as this form in 0 external field near TC. Okay, so what is that? How does that explain the physics of the system? So let's go to this thing. Let's stick this thing back down there. Okay. So this little diagram tells you what is the behavior of this potential, this Landau free energy, what it looks like as a function of temperature and external magnetic field. So this is let's graph L as a function of H and T. And that's what we see here. And we want to do that. And then the question we want to ask is what value of eta is the global minimum? So I'm sorry that this is so small. So why don't I make it bigger on the next page? So you can all see it. Okay, so that's over here. Okay, so let's first of all have a look at this row. H is equal to 0. Okay, so what happens if I'm above TC? There's only one minimum. So here I'm above TC. There's only one minimum. It's this one here, because L looks like a quadratic function plus a quartic. So it's going to look like an upside down parabola, but it goes up a bit steeper than a parabola would. So that's what's going to happen. If, on the other hand, T is less than TC, then what that means is this term over here, for T less than TC, little t is negative. So what's going to happen is near the origin, near eta equals 0, this thing goes down as minus eta squared. So that looks bad. But then at large eta, it goes back up again because of the term eta to the fourth. So this term eta to the fourth, this is important for large values of eta. And the term minus eta squared is important for small values. And so what happens then is the function, so this part of the function is due to the eta to the fourth term, and this term over here is due to the minus eta squared term, and then the actual minimum value are these two values here, this one and this one. They're two degenerate minima. They correspond to eta is plus or minus the square root of A over B. So over, maybe I can put this over here. So eta min is equal to minus a t over b square root, and then there's two of them, so there's a plus or minus. So I've got two degenerate minima like that. Can you see that? Can you see what I wrote in blue? Is it too faint? You can see it? Okay, I'll try to use a darker color. Okay, now let's ask what happens when I have an external magnetic field. So it doesn't really matter which way we do it. If the external magnetic field is positive, we get the graphs that look like this. If the external magnetic field is negative, we get what's up here, but everything is just shifted to the minus, to the negative side. So now you can see what happens when there's external magnetic field is that the transition is kind of looks weird. When you go through TC, nothing special happens here. The solution doesn't change sign, but over here, it would have been more helpful if I'd drawn this further. If I go much further below TC, then my curve would look like this. And then suddenly what would have happened is the solution would have now dropped to this point over here. It would have gone from there to over here. So remember what we're always after is the global minimum of the Landau free energy. And as you change the field and you change the temperature, what may happen is that the global minimum might jump discontinuously from one value to another. So here we have a smooth, continuous transition. And here you have the possibility of a discontinuous transition, discontinuous jump. And so we predict different behavior depending on H and T. So we predict different types of phase transition with different consequences that come out. Okay, so that would be a really bad choice of color. Okay, so what we've learned is that that this description qualitatively captures the phase transition at T equals Tc and the emergence of an order parameter below Tc, and it predicts that the magnitude of the order parameter grows as the square root of Tc minus T over Tc, as T is less than Tc. So we make a semi-quantitative prediction. This prediction isn't bad. Turns out not to be quite correct for all sorts of subtle reasons to do with the normalization group effects and things like this. But we don't want to focus on that in this course. So last quarter, we spent the entire quarter just answering whether this result is correct, which it isn't, and why it's not correct and how to improve it. And actually to do better than the simple argument I've shown you here is a huge big problem. You can do it, and it's a huge amount of work. And if you're the first person to do it, you got the Nobel Prize for doing it. Okay, so we're not going to worry about that, because what we want to know is what happens when you're way below Tc. And when you're way below Tc and you have a continuous symmetry, it turns out that there's a completely different physics that comes into the problem. And that's what we're going to want to talk about next. Okay, so I want to now change gears and talk about space. So that's the next thing we're going to do. So up to now, we pretended we had an order parameter that was just a constant number, independent of space. And now we're going to say that this eta is now going to literally be an eta that depends upon space. So what do we need to do for L? So before, we had L was just the volume of the system times our Landau free energy density. Now we're going to say that L is the integral over space, of an integral over d dimensions of some quantity, which now depends on a variable eta of r, in a way that we need to figure out. Okay, so that's the biggest change, that we're allowing eta to depend on R. And so L will depend upon eta as a function of R. And this kind of object is what is known as a functional. So what is a functional? Well, what is a functional? Well, what is a function? So the answer is, well, a function takes a number, say x, and produces another number called f of x. So it's a map from one function to another. Okay, that's what from one value, from one number to another number, that's what a function is. Okay, so what is a function now? It takes a function and turns it into a number. Okay? So you're used to seeing functionals. You've seen them before. So for example, here's the simplest one. I is the integral a to b of f of x dx. Okay, this is a machine. You put into the machine what is the value of this. So you specify the function f of x, meaning the function at every point in space between a and b, and then what you get out is a number. And that's what a functional is. So our Landau free energy is a functional. Okay, so that's just the nomenclature. So now the question we want to ask is, what principle can we use to construct the spatial behavior? So now we have to think about what we're dealing with. We're talking about a physical system which has got some low level of description, like spins on a lattice or atoms in a gas or something like this, or atoms in the fluid. And now we're saying what we want to do is we want to answer questions like, for example, why can you hear me? How do you hear the sound waves that are coming out of my mouth? How do we describe those properties? Where the wavelength of the sound waves is much greater than the spacing between the atoms, so I can ignore the existence of atoms. Or I'm looking at spin waves in a material, in a magnetic material, in a condensed matter physics lab, and I'm looking at some waves of magnetization that are flowing through the system, perhaps time dependent, and the wavelength of those waves is much greater than the spacing between the spins or the atoms on which the spins exist. So we're looking at long wavelength behavior. I.e., lambda is much greater than, say, the atomic spacing. Okay? So sometimes we use the term hydrodynamic description. Why do we call it that? Well, the first hydrodynamic description was made by Euler and then by Navier and Stokes. So they wrote down the equations of motions for a fluid. Okay, and those equations of motion for fluid, you use them every time you get into a car, every time you get into an airplane and fly somewhere, you're using those equations. The people who wrote down those equations 200 years or so ago, those people knew nothing about the existence of atoms, and yet those equations work perfectly well, okay, for very extreme conditions, okay? So we didn't even know about what matter looks like on the local scale. So what can we say about, say, a fluid or a system at large scales when we look at it? Well, so first of all, on the long wavelength behavior, what that means is that the system is going to be isotropic. It's going to be spatially isotropic. Okay, that would be the first term, the first thing. So that means whatever terms we put in should be rotationally symmetric. Another thing we know is that they should be analytic for all the reasons that we talked about before. And then another thing we know is, what is the physics of this? Why don't we just say, for example, why don't we just say that L of eta goes to L of eta of R? Just wherever you had eta squared, e to the fourth, just replace it by the local value. You could do that, but it would be wrong. And the reason is that if I have gradients of something, then those gradients cost energy. So you need to have a term that penalizes energy gradients. Remember that in equilibrium, the system wants to be spatially uniform. So in order for it to be spatially uniform, you need to have a term that says if the system is not spatially uniform, that raises the energy. So gradients in eta need to raise the energy of the system. Otherwise, the equilibrium state will not be spatially uniform. Okay, so what does that give us? So the gradient terms that we could have to be something like grad of eta. So we have to have things like that. Has to depend on the gradient of eta. But the other thing that we need to know is that L is a scalar and grad eta is a vector. So that can't be, it can't just be a term that is grad eta. It's got to be a term that is a scalar. So the only scalar that we can make out of grad eta is grad eta squared. And this is isotropic, analytic, and grad eta squared equals 0 in equilibrium. So what we've discovered then is that if we're trying to understand the generic behavior of systems which have order, the hydrodynamic description of emergent order must be of the form L is equal to the integral over a volume ddr of some term, some coefficient, grad eta squared plus L of eta of R, like that. And this is the foundation for our theory for ordered matter. So a long wavelength description has to be of this form. Okay, so it's 3:20, so I'm going to finish today's lecture. So next time, what I've shown you here, just to explain the basic ideas to you, was just using discrete symmetry, an Ising model. So next time, what we're going to do is generalize this to a continuous symmetry. This generalization to continuous symmetry is not just saying, well, we just make it more general and so on. It actually has there's a very profound difference in the way that the system orders. And that's why we can use this description to study the quality of nature of matter very accurately, of ordered matter when you have a continuous symmetry. So we're going to talk about that next time. Okay, so that's it for today. Let me turn off the recording.